There are two important subspaces related to a linear transformation. And actually, you know about both of them already. When I describe them, hopefully they will look familiar. So let's let T be a linear transformation from a vector space V to a vector space W. So V is called the domain, and W is called the codomain. So those aren't the two subspaces, those are spaces. We're going to look at subspaces of those. So define T of capital V to be the set of all things of the form T of little v, where little v is a vector in capital V. So that's the things in W that we actually get by applying T to something in V. And that might not be all of W. It might be. So this may or may not be all of W. For example, let's let A be the matrix that has 2 1s and 2 0s in it. And let's let TA be the map from R2 to R2, which is left multiplication by A. So take a vector, left multiply it by this matrix. So then if we apply that to x1, x2 as a vector, that's 1 1 0 0 times x1 x2, which is going to be x1 plus x2 0. And the set of all vectors we get by applying TA, by left multiplying by A, is not going to be all vectors in R2, because the second component is definitely going to be 0. So TA of R2 is going to be, well, if x1 and x2 are real numbers, then their sum could turn out to be any real number. So it's going to be all vectors of the form A0, where A is a real number. So we call this set T of V the range of T. And the range is always a subspace of W. And it's easy to check. So we just need to check that it's closed under scalar multiplication and closed under addition. So let's look at two elements in T of capital V, which is also part of W. So we apply T to the elements V1 and V2 in the vector space big V. So then we're wondering, is T of V1 plus T of V2 equal to T of something? Well, it's equal to T of V1 plus V2 by the linearity of T. So T of V1 plus T of V2 belongs to the range capital T of capital V. Now let's check that it's closed under scalar multiplication. So if V is an element of the vector space capital V and C is a scalar, then what do we know about C of TV? Is that in the range also? Well, by linearity, C of TV is T of CV, which is T of something. So that belongs to the range also. So since the range is closed under addition and closed under scalar multiplication, then it's always a subspace of the space it's inside, which is W. Now another subspace associated to the map T is called the kernel of T. So we write KERT, that stands for kernel of T, and that's all of the vectors x in the vector space V such that T of, actually let me call this little v, all the vectors little v in the vector space capital V such that T of little v is 0. So all the vectors that get mapped to 0. Now this is a subspace not of W but of V. The reason is if we have two vectors in the kernel, let's say V1, T of V1 is 0 and T of V2 is 0, then T of V1 plus V2, so is V1 plus V2 in the kernel? Well, T of it by linearity is T of V1 plus T of V2, which is 0 plus 0, which is 0. So I guess it's closed under addition. And then scalar multiplication is easy to check. If T of V is 0 and C is a scalar, then how about CV? Well, T of CV is by linearity C times T of V, which is C times 0, which is 0. So CV is in the kernel whenever V is. So since the kernel is closed under addition and scalar multiplication, the kernel is a subspace. Alright, so far I've talked about abstract linear transformations from one abstract vector space to another. Let's talk about the coordinate version. So remember, every linear transformation is left multiplication by A. So every linear transformation, I guess I should say T from V to W, is left multiplication by A once we choose bases, let's say B and C, for V and W. So let's look at the range and the kernel of transformations of the form T sub A. The range of T of A equals the set of all TA of V for V in Rn. So once we pick coordinates, we're going to replace V and W with Rn and Rm, where n and m are the dimensions of V and W. So this is all the expressions of the form Ax, where x is an Rn. X is the coordinate vector of V. And actually, I guess I should say V is really in the vector space capital V, and its coordinate vector is really in Rn. But Ax, as x varies over all real vectors in Rn, is just all linear combinations of the column space of A. Sorry, all linear combinations of the columns of A. Which is the column space of A. So range is really the coordinate-free version of column space, which we already know. Now let's look at what the kernel of the coordinate version is. So the kernel of TA is all of the vectors such that TA of V is 0. So all of the coordinate vectors x in Rn such that Ax equals 0. Well, we know all that already. That's the null space of A. So in the coordinate version, range and kernel are really just the column space of A and the null space of A. I'm thinking I want to rewrite this again. So if TA is left multiplication by A, then I really want the coordinate vector here already. So I'm going to replace this V with X, and X is in Rn. And TA is really a map from Rn to Rm. So I really want this to be the X, the set of all X in Rn, such that TA of X is 0. And then that's all the X in Rn such that AX is 0. So when I switch from the linear transformation to T to TA, then I really should be switching to the coordinate vector of the original vector that we were thinking of. Now, a fact about the range and the kernel is that the dimension of the kernel of T plus the dimension of the range of T equals n, the dimension of the first vector space V. So T is a map from V to W. The dimension of its kernel and the dimension of its range sum to n, the dimension of V. And the reason is that if we choose bases B and C for V and W, then T becomes TA, where A is the matrix of T with respect to the bases B and C. Then the dimension of the kernel of TA plus the dimension of the range of TA equals the dimension of the null space of A plus the dimension of the column space of A. The dimension of A is the nullity of A. The dimension of the column space is the rank of A. And we know that this is n by the nullity and rank theorem. All right, now let's do an example of this. And let's revisit the example that we did earlier of a linear transformation. So we'll call the earlier example where V is all of the 2 by 2 matrices with the diagonal summing to 0. In other words, all of the matrices of the form A, B, C, negative A, where A, B, and C are real numbers. And we'll define T from V to itself by A gets mapped to the matrix of all ones times A minus A times the matrix of all ones. In other words, T of this typical matrix A, B, C, negative A equals C minus B, B minus C down there, and negative 2A up here and positive 2A down there. So let's find the range of T and the kernel of T and their dimensions. Well, the range of T is all the things we get by applying T to elements of a vector space. So it's all the T of A, B, C, negative A, where A, B, and C are real numbers, which is all the vectors of this form, all the matrices of this form, all the matrices of the form C minus B minus 2A, 2A, B minus C, where A, B, and C are real numbers. If A, B, and C are real numbers, then that difference C minus B could be any real number. And B minus C is going to be whatever the opposite of C minus B is. So we'll get some real number D and its opposite on the diagonal. And then off the diagonal, if A is a real number, then 2A is any real number. And so these numbers could be any real numbers as long as they're the opposite of each other. So let me write E and minus E. So the matrices we get are going to always have these entries opposite and those entries opposite. And once we pick one number for the absolute value of these two and one number for the absolute value of those two, then we've completely specified the matrix. So this space has a basis with two elements in it. There's one very natural choice. So a natural basis for the range of T is 1, 0, 0, negative 1 and 0, 1, negative 1, 0. So apparently the range has dimension 2.